You know, we always think about gravity like it's this big fundamental force of the universe.
Right.
But get ready for a real mind-bending deep dive today.
Oh, yeah.
Because you wanted to explore this paper that basically flips that whole idea on its head.
Totally.
We're talking about physicist Erik Verlinde's On the Origin of Gravity and the Laws of Newton.
Okay.
And he suggests that gravity might not be fundamental at all,
Yeah.
but emerges from something way deeper, information itself.
It's a pretty radical idea.
Right.
Yeah. To think that gravity is just like a side effect of the universe's tendency to just become more disordered,
Okay.
to increase its entropy.
Hold on. So instead of picturing gravity as like the Earth pulling me down,
Uh-huh.
I should imagine it's more like the universe pushing me
In a way.
towards a state of higher entropy.
Uh-huh.
Okay. I'm already feeling a bit lost in space here,
I get it.
to be honest.
It's a big shift in thinking, for sure.
Yeah.
To understand Verlinde's argument, though, we first kind of need to grasp this concept of an entropic force.
All right. It's an entropic force.
Yeah, so think of it like this.
Okay.
Imagine a polymer molecule,
Yeah.
a long chain of atoms just floating in some hot liquid.
I'm picturing
A
it.
polymer naturally wants to, curdle up. Right?
Yeah. I can picture that kind of like a tangled up string.
Exactly.
Mm-hmm.
And there's a reason for that.
What is it?
There are just way more possible configurations for the polymer to be all tangled up
Okay.
than for it to be stretched out.
Makes sense.
So it's just a matter of probability.
Uh-huh.
So to stretch it out, you have to apply a force,
Mm-hmm.
right?
Yeah, you'd have to pull.
And that force.
Yeah.
It's essentially the polymer resisting that decrease in its entropy.
Okay.
It's a level of disorder.
Interesting.
Kind of want to go back to that messy, high entropy state.
Okay, so the force isn't like some mysterious attraction.
Right.
It's just the odds playing out at a molecular level.
Exactly. It's like a statistical effect.
Wow.
That emerges from the behavior of all those tiny atoms in the polymer.
So cool.
Kind of like gas pressure in a way.
Oh, yeah.
It's not that the individual gas molecules are pushing,
Right.
but their constant bouncing around creates the pressure we experience.
Yeah, okay. I think I'm starting to get this idea of an entropic force.
Good.
But how does this connect to gravity?
Right.
I mean, we're talking about planets and stars here,
Yeah, that's the thing.
not tiny little polymers.
That's where things get really mind-blowing.
Okay.
Verlinde proposes that gravity might actually be an entropic force on a cosmic scale,
Whoa.
arising from the way information is distributed throughout the universe.
Okay.
And to do this, he uses this concept of holography.
Okay. Holography.
Yeah.
Isn't it like those 3D images you see on like credit cards and stuff?
Kind of, but imagine this.
Okay.
All the information about our 3D universe,
Everything.
everything we see and experience, is actually encoded on a distant 2D surface,
What?
like a cosmic blueprint
Okay.
projected into 3 dimensions.
So our reality is just a projection of information from some 2D surface.
That's the idea.
That's a lot to process.
I know, it's crazy.
Is there any evidence to support this idea, or is it just like a cool thought experiment?
Well, actually, there are some intriguing hints from studying black holes.
Oh, really?
Yeah, you see, Verlinde draws connections between black hole thermodynamics
Okay.
and something called the ADS-CFT correspondence,
Wow.
which provides mathematical support for this holographic principle.
Whoa, those sound like some seriously complex ideas.
They are.
Maybe you could break those down a little for us.
Sure. So the ADS-CFT correspondence is this amazing mathematical duality
Okay.
that shows this link between gravity and a particular type of space-time
Okay.
called anti-de Sitter space, or ADS,
ADS got it.
and a quantum field theory, or CFT,
Okay.
that lives on its boundary.
So it's like two different spaces.
Yeah, think of it like a dictionary
Okay.
that's translating between 2 languages,
Interesting.
one describing gravity and the other describing quantum particles.
So in a way, it's saying that gravity in this special kind of space can be described by a theory that doesn't even have gravity in it.
Exactly.
Wild.
It suggests that gravity, at least in this context,
Yeah.
is not a fundamental force,
Okay.
but emerges from the interactions of these quantum fields on the boundary.
So gravity as we know it could be something else entirely.
In a way, yeah.
Okay. That's already pretty wild.
Yeah.
But how does this connect back to our universe
Right.
and Verlinde's idea of gravity as an entropic force?
Well, Verlinde takes inspiration from this ADS-CFT correspondence,
Okay.
and he applies it to our universe,
Okay.
even though it's not exactly an ADS space.
Right.
He envisions these holographic screens
Holographic screen.
that contain information about the distribution of matter and energy in space.
So these screens are like those 2D surfaces from the holographic principle?
Yeah.
Where all the information about our 3D world is stored?
Exactly.
Yeah.
And Verlinde proposes this key link.
What's that?
That changing the distribution of matter and energy
Okay.
alters the information content, the entropy on these screens.
Interesting.
It's like adding more details to the blueprint, which changes the 3D projection.
Okay, so changing the position of matter changes the entropy on these screens.
Right.
But how does that create a force, like something that we feel as gravity?
I know.
This is where I really start to get lost.
So Verlinde argues that moving a mass,
Okay.
like, say, lifting an apple, changes the entropy on these holographic screens in a specific way.
Okay.
And the force required to move that mass to overcome that change in entropy.
Yeah.
It turns out it matches exactly with Newton's law of gravity.
Wait, seriously?
Yeah.
So you're saying the force we experience as gravity emerges from these microscopic changes in information on some distant screen?
That's the core of Verlinde's argument.
That's crazy.
And it's not just that the numbers work out. The concepts fit together in this surprisingly natural way.
Right.
And the math beautifully reflects that connection.
Okay, but Newton's law of gravity describes a force between two objects.
Right.
How does Verlinde's theory explain that interaction?
Okay.
Are the objects somehow communicating with each other through these holographic screens, or what?
That's a great question.
Yeah.
And it brings us to another fascinating aspect of Verlinde's theory.
Okay.
He suggests that the way objects influence each other gravitationally can be understood by looking at how they affect the total entropy of the system.
The total entropy.
Yeah, so imagine a group of particles just scattered throughout space.
Okay, I'm picturing it.
Each particle kind of contributes to the overall entropy of the system. Right? Now, if you move one of those particles, you change the distribution of matter and energy.
Right.
And that affects the total entropy.
So it's not just about the individual objects and their attraction, but about how they collectively contribute to the entropy of the whole system.
Exactly.
Okay.
And those holographic screens we've been talking about, we can imagine placing a screen around this group of particles.
Okay.
And the total entropy of the system is encoded on that screen.
Got it.
And Verlinde shows that the entropic force acting on each particle can be calculated by looking at how its presence affects the information on that screen.
So in a way, each particle is talking to the others through these changes in entropy on the holographic screen.
That's one way to think about it, yeah.
That's a wild way to think about gravity.
It is.
But what determines where we place this imaginary screen?
That's the beauty of it.
What is it?
It doesn't actually matter.
Really?
You could choose any screen that encloses the system of particles.
Yeah.
And you'd get the same answer for the entropic forces.
So it's like a universal law?
In a way, yeah.
Wow.
The choice of screen is just a choice of scale.
Okay.
Remember, we're talking about the emergent nature of space itself here.
Right.
The underlying information and entropy are what matter.
That's pretty elegant.
Yeah.
But we've been mostly talking about Newton's classical view of gravity here.
What about Einstein's general relativity?
Right.
With curved space-time and all that.
Yeah.
Does Verlinde theory work in that context too?
It does.
Right.
In fact, it's even more remarkable in the context of general relativity.
Okay, how so?
Verlinde shows that his approach actually leads to Einstein's equations.
No way.
The very equations that describe the curvature of space-time.
Wait, hold on. You're saying this theory, based on entropy and holographic screens, can actually reproduce Einstein's equations?
That's right.
That's a huge claim.
It is.
And
It gets even wilder.
Okay, lay it on me.
Remember how in general relativity, gravity affects time and light?
Yeah.
We talk about this redshift effect where light's wavelength gets stretched by gravity.
Right.
Well, Verlinde connects that redshift
Okay.
to entropy gradients on his holographic screens.
So the redshift isn't causing the change in entropy.
Right.
It's the other way around.
Exactly.
The change in entropy on the screen is what leads to the redshift we observe.
Precisely.
And this connection is especially profound when we consider the equivalence principle.
Oh.
Einstein's mind-blowing insight that gravity and acceleration are essentially two sides of the same coin
Right.
in Verlinde's framework.
Yeah.
Both gravity and acceleration emerge from this deeper connection to entropy and information.
Yeah.
Neither one is truly fundamental.
Okay. My brain is officially doing backflips.
I know, it's a lot to take in.
But if everything is emergent,
Yeah.
How do we even define things like mass and energy in this new picture of gravity?
Excellent question.
Yeah.
So Verlinde uses those holographic screens to define mass in a way that's consistent with general relativity.
Okay.
He uses this concept called Komar mass,
Komar mass.
which is a way to define mass in a curved spacetime.
Okay, forgive me if I'm being dense here, but what exactly is Komar mass?
Sure.
Is it like measuring the weight of an object?
Not exactly. Think of it more like Gauss's law from electromagnetism,
Okay.
but for gravity.
Gauss's law for gravity.
Yeah. So Gauss's law says that the total electric charge enclosed within a surface is proportional to the electric flux through that surface.
Okay, I vaguely remember that from physics class.
Right. So similarly, the Komar mass is related to the flux of gravitational energy through a closed surface.
Okay, so it's a way to define mass based on the gravitational effects it produces, even in curved spacetime.
Exactly.
Got it.
And by applying his ideas about entropy and information to this Komar mass,
Okay.
Verlinde derives a generalized version of Gauss's law for gravity.
Wow.
It really demonstrates how these deep connections between gravity, entropy, and information naturally lead to equations that are consistent with what we already know from general relativity.
That's incredible.
It is.
But let's be real here.
Sure.
This is still a very theoretical framework, right?
Of course.
So how does it actually work in the real world?
Well, that's the exciting part.
What is it?
Verlinde's theory isn't just a mathematical exercise.
Okay.
It leads to potential observable effects. For one, it suggests that gravity might not be perfectly constant, as we've always assumed.
Wait, are you saying gravity could actually vary in strength?
It's a possibility.
Wow.
There might be tiny fluctuations in gravity strength, depending on local variations in entropy and energy.
So you're saying gravity might be a little bit fuzzy at very small scales?
Kinda, yeah.
Could we actually measure these fluctuations?
That's the hope.
Wow.
If these fluctuations exist, we might be able to detect them with extremely precise measurements.
That would be amazing.
It could be a huge breakthrough in our understanding of the universe.
Okay, I'm on the edge of my seat.
Yeah.
But even if those experiments are a long way off, Verlinde's ideas already offer a completely new way of looking at the universe.
Absolutely.
It really does.
It shifts our focus from forces to information,
Right.
from individual objects to this interconnected web of entropy.
It's a humbling thought, isn't it?
It is.
All the complexity and beauty of the universe, from planets and stars to galaxies and black holes.
Yeah.
Might just be the universe trying to be as lazy as possible.
It's a beautiful way to put it.
It is.
It highlights the profound interconnectedness of everything in the universe.
Yeah.
How even the simplest actions, like dropping an apple, could be part of this grand cosmic dance of information and entropy.
Speaking of dropping apples, didn't Newton get into a bit of a debate about gravity with another scientist?
It did?
Robert Hooke, right?
Yeah.
Something about action at a distance?
You're right. Newton's idea of gravity as an action at a distance where objects instantly influence each other across empty space was highly criticized by Hooke.
Oh, yeah. He believed forces needed a direct mechanical explanation.
Right, like the tension in a spring.
But now with Verlinde's theory, gravity might be more similar to Hooke's elastic force than we ever imagined.
It's true.
It's like those historical rivals might actually be converging in this universe governed by holography and entropy.
It's a funny thought.
What a twist.
It really makes you appreciate the interconnectedness of scientific ideas across centuries.
It does.
Yeah.
But let's come back to the present.
Okay.
Verlinde's paper itself acknowledges some open questions. Like, how does this all work in areas of weaker gravity far away from black holes?
Right.
Does he offer any explanations for that?
Right, because so much of what we've talked about seems to revolve around these extreme gravity environments.
Yeah.
Does Verlinde's theory only work near black holes?
Well, that's one of the big challenges,
Yeah.
applying these ideas to weaker gravity regimes.
Right.
Like the kind we experience here on Earth.
Right, exactly.
Verlinde suggests that things might work a little differently in those situations.
Okay.
Remember how Planck's constant, that fundamental constant from quantum mechanics, kind of disappeared from the equations earlier?
Yeah, it felt like a magic trick.
Right.
1 minute it was there, the next it vanished.
Exactly.
So where did it go?
Well, that's the mystery.
Okay.
Verlinde suggests that in these weaker gravity regimes,
Okay.
Planck's constant might actually play a more significant role.
It could be that the effective strength of gravity varies slightly.
Oh, God.
depending on the specific energy and entropy configurations in a given region.
Hold on. Are you saying gravity might not be as constant as we think it is?
It's possible.
That it could actually fluctuate depending on these quantum effects?
That's one of the intriguing possibilities that emerges from Verlinde's theory.
Wow. And if these fluctuations in gravity exist, could they have implications for some of the bigger mysteries in cosmology?
Potentially, yeah.
Like dark matter and the accelerating expansion of the universe?
Exactly.
Wow. So we're talking about potentially rewriting our understanding of the entire universe.
It's a big idea.
It is. But before we get ahead of ourselves, what are some of the other open questions that Verlinde's paper brings up?
One of the biggest challenges is understanding the exact nature of those holographic screens.
Right.
What are they made of?
Yeah.
Where are they located?
Huh.
How do they interact with matter and energy in our 3D universe?
Right.
These are all questions that Verlinde's theory doesn't fully answer yet.
Yeah. It sounds like there's still a lot of work to be done to flesh out these ideas.
Definitely.
But even if some of the specifics need to be revised or refined, the core concept that gravity could be an emergent phenomenon connected to information is incredibly powerful.
Absolutely.
It completely changes how we think about the universe.
It's a true paradigm shift.
Yeah.
It challenges us to move beyond thinking about forces as fundamental.
Right.
And to consider information as the building block of reality.
And it all goes back to this idea of entropy, this tendency for the universe to become more disordered.
Right.
It's like the universe is constantly trying to find the most probable, the messiest state. And gravity, as we experience it, is just a consequence of that drive towards maximum entropy.
It's a beautiful way to think about it.
It is.
It suggests that everything in the universe, from the smallest particles to the largest structures, is connected through this intricate web of information and entropy.
It really makes you wonder, what is information?
Yeah.
And how does it give rise to the reality we experience?
Those are big questions.
These are some profound questions that Verlinde's work brings to light.
It really blurs the lines between physics and information theory,
Yeah.
suggesting that they might be two sides of the same coin.
Well, I think you've officially blown my mind today.
Glad I could help.
Next time I feel gravity, I'm going to imagine it as the universe gently nudging me towards a more probable state.
I like that.
It might even make doing the dishes seem a little less daunting.
Right.
And who knows, maybe someday we'll look back on this as the moment when our understanding of gravity took a giant leap forward.
Possible.
All thanks to the idea that it's not a force, but an emergent phenomenon born from information itself.
It would be quite a shift in our thinking.
A huge thank you to expert speaker for guiding us through this incredible deep dive into the mind of Erik Verlinde.
My pleasure.
It's been a wild ride.
It has.
And to you, our intrepid listener, keep questioning, keep exploring, and never stop diving deep into the mysteries of the universe. Until next time.